Hi, I'm Sean Charlesworth.
And I'm Jeremy Williams.
I'm the 3D printing and fabrication specialist for Tested.
I like to tinker with code and electronics.
This show is about making things.
It's about the journey from the computer screen
to something that you can actually hold in your hands.
From bits
to atoms.
Hey Sean.
Hi Jeremy.
So we have the Tested live show coming up.
Yep.
Tested does a live show every year. We've done this for 3 years in the past. This will be our 4th year. We're at the Castro Theater in San Francisco.
Yep. End of October.
Fills the auditorium.
Yeah, I'm shocked how it's packed.
It's amazing. It's so much fun. And you and I this year have been asked to bring Bits to Atoms to the main stage.
I know, it's my first time on stage. I'm a little nervous.
It's gonna be a ton of fun. So we have our choice about what to do. We could take one of our past projects and talk about the creation of it. The theme of the show is deconstructed.
Right, so like the process, which it seems to be what people are really enjoying about our show, is that we're revealing a lot of that and the mistakes.
Exactly. Mistakes are a big part of the process.
Yeah.
Or we could go out on a limb and make something entirely new that debuts and is first used and tested on stage at the Tested Live show.
Sure, why not?
I could name a few reasons why not, but I think the excitement of doing that is worth it.
Yeah, and to be honest, we've actually chatted about this a little bit.
We have.
So yeah, so we have some ideas for this, and we thought something interactive might be fun.
I'm a big fan of involving the audience. I think clapping is that's nice of them to do, but if you get them involved a little bit more, it becomes more exciting for everybody. Plus, if we get some audience interaction, then it becomes like even more of a tightrope show for whatever it is that we make.
Yeah, so tell them what you had in mind.
So I thought, well, first of all, I was thinking it'd be fun to incorporate stepper motors. Because
I love stepper motors.
See, I love them too, although I've never used them. Yeah. But they make things move that I love. So
3D printers, they're using there a lot. They're very precise motors that you can do very precise movements with. So therefore, they're really good for the XY on 3D printers, stuff like that.
Right, exactly. And they're very easy to control with the kind of technology that I'm familiar with, microcontrollers and that kind of thing. So I was thinking, how could we get the audience involved in controlling stepper motors? That's kind of the genesis of this. So we have a few things here. I made a controller here using a Teensy and a controller board, a stepper motor controller.
Okay.
And we have a stepper motor itself. And I had these out on my desk, and I'm thinking, what if the audience could play a game?
Okay.
Using the stepper motors, right?
Yep.
And what if that game was the first game, right? You know the story of the very first video game, Tennis for Two?
I don't think so.
So this was made by a nuclear physicist in the 1950s, and he made the very first video game, which is essentially like an early version of Pong.
Okay.
On an oscilloscope screen. It's beautiful. It's a beautiful work of art, and they showed it at a show, and it was remarkably popular.
Okay.
Foretelling, video games.
Oh yeah, yeah.
And so this would be Tennis for 2000. Right?
So how does this work?
Well, the ball would be a physical object.
Okay.
And it would move on a board in X and Y.
Right.
Just like a 3D printer.
Right.
Right? So that there is the stepper motors.
Yeah.
And we would be able to track where it is because of the very precise positioning control that you have with stepper motors.
Okay.
So we know where it is. Now we just add 2 goals on either side. That is basically, an LED strip with a bar that goes up and down that the audience would control. The left side of the audience controls the left goal, the right side, the right side.
And how are you picturing that they control this?
I was picturing that they would control this with their mouths, with their voices, with their humanity.
So mics, I'm picturing mics, and whichever side is yelling more or whatever, it would control.
I'm imagining that the louder they yell, the higher the goalie goes.
Oh, fascinating.
Right?
Okay, so Pong, we got the paddles, right? So if they're like, oh, it's just gonna be right?
Yeah, exactly. And they have to work together on this.
Right.
So it's not. We'll see if they can do that because they don't want to overcompensate. We'd also have to do some weird filtering, or maybe that's just a matter of getting the right microphones, because we don't want the left side of the auditorium to control the right side of the auditorium, right?
True, we don't want any sabotage there, yeah.
So I'm thinking like we'll have to get the left side and the right side to be loud one at a time, and then we'll use their loud to be the height, the high point of their goal, but also the low point of the opposing team's goal. Does that make sense?
Yes.
Because we want them to be as loud as they can, and that won't affect the other side. So that would be the low point of the other side. So the other side has to be at least that loud before it starts to go up. And then we have Pong.
Yeah, this is totally gonna work, yeah.
We've said that before.
Hey, we've always managed to pull it off. So I feel that, you know, this will be no different.
Now,
so,
I've made a few video games before, very, very simplistic things.
Yeah.
So I'm not terribly worried about the Pong code, getting it to bounce in the correct, you know, angle and things, and syncing up where the ball is and where that LED strip is. I think that should be doable.
Right.
But I've never messed with stepper motors before, and so I don't know about the physicality of building this structure.
Right, because we have the mechanical aspect where we basically need an XY gantry. So it's a plotter system. And once again, very similar to how 3D printers work. It's an XY plus a Z for height.
Or a laser cutter, right?
Yeah, and yeah, it'd be more like a laser cutter. Well, actually, laser cutter has Z too, but. So we need some kind of frame, motors, motor mounts, and all that stuff to control basically the ball. Now, what are you, and you said for the paddles themselves, you're picturing not a mechanical thing, but like more like LEDs,
right,
where it's lighting up, right?
Really dense LED strips.
Okay, all right. So yeah, so let's delve into that. So, and you brought me, why don't you show me what you brought me here?
Yeah, so this is a very simple test of a stepper motor. Now, I have learned.
Oh wait, should this be unplugged first?
No, this should be unplugged.
Oh, okay.
I have learned exactly what you're referring to.
Yeah.
Is never unplug or plug in a stepper motor to its controller while it's plugged in.
Got it.
Because that destroys the controller.
That would be bad.
All right. So yeah, this is red button makes it go one direction. Green makes it go the other, right?
Okay.
And this is as fast as this goes. I'm a little bit concerned about the speed there. There's some things that I can do to speed it up.
Right.
For instance, it's currently running at what they call full step mode. And this is all new to me, stepper motors. But one step of a stepper motor is 1.8 degrees.
Oh.
Did you know that?
I did not know that. I did not know that.
I did not know that. But that means that it's 200 steps for a full 360.
Right.
Right? Which is easily divisible by half or a quarter, so you can get very specific directions.
Okay.
But modern controllers can do what they call micro-stepping. So you can do half steps, which means you send 2 pulses to go a full step.
Okay.
And that energizes the magnets in here at different rates in order to make it move a little bit rather than a full step.
Okay, okay.
And you can do quarter steps, 8 steps.
I did not know that.
It's really interesting. And just back to what I just said, this is actually driven by magnets. There's different poles in there that grab the wheel, essentially, and make it spin around. And nothing touches the actual shaft.
Really?
It's
I
all
did not
done
know that.
magnetically.
Wow, that's really impressive because stepper motors also tend to have a lot of torque behind them and everything.
Exactly,
too, so,
exactly.
Yeah.
And they have the most torque, I've learned, when they're still. When they're moving, as they get faster and faster, the torque actually decreases because they're not aligned with one of those magnetic poles.
Got it.
When it's still, it is.
Huh.
So that's interesting, and so that's also a matter that we'll have to experiment with to see how much torque do we actually need.
Right.
So it's kind of a trade-off between speed and torque. But the micro-stepping should allow us to get a little bit faster. We can ramp up a little bit faster. So we can experiment with that. I'll experiment with that. And yeah.
So I'm also picturing if we're gonna have this on stage, this needs to be relatively big so that it can be seen well. How big are you envisioning?
I mean, I'd love it to be the size of the movie screen. that would be amazing. But I'm thinking the really dense LED strips that I'd like to use are 144 LEDs long, and they come in metered lengths.
Okay.
There must be a way to get longer than that, but they're very easy to find in meter length. So maybe the goals are a meter high, and then Sky's the
whatever
limit for the
width.
for the
Okay.
X.
All right.
But maybe like a 4:3 ratio to be like Pong.
Yeah.
Or 16:9 or whatever you like.
Yeah.
Does that seem reasonable?
Is that
too big?
No.
Okay.
I think we can do it. I think we do it. It's interesting how people work. Like I'm always very, very cautious. So my initial reaction to a lot of projects is like, I don't know, but I think we can totally pull this off. We've managed to do everything else. It doesn't seem too crazy.
Yeah.
It's basically building on a lot of technology that is out there in 3D printers. So I think that mechanically we can work it out as well, and you've always pulled off the code. So yeah, I'd say we go for it.
Knock on wood. I think this could be a lot of fun. I'm really excited to see the audience interact with something that we have working on stage. Now, it's like every development, it's a house of cards.
Sure, absolutely.
I mean, this could entirely go wrong. And hopefully there's still a story there.
And there will be, regardless of what happens, it will be a fun story. And, as Adam says, failure is always an option.
Let's keep that option open, shall we? All right, so I'll see you in a couple weeks. I'll delve into the software and you delve into the structure.
Yeah, I'm going to take this with me so that I can test some different mechanical stuff with the stepper motor.
Cool.
And we'll meet back up and see what we come up with.
All right.
All right, Jeremy, it looks like you've been very busy. We got a multitude of boards and wires going on here and some giant LED strips.
Yeah, and I learned a little bit.
Yeah.
So first of all, the stepper controller that I gave you was using something called the Easy Stepper, I think it's called. Mm-hmm. Anyway, it's very easy, and it only provides 750 milliamps of power to the stepper motor.
Okay.
I found out that these guys, these little ones, are actually more of a favorite in the 3D printing community, and they deliver twice that, an amp and a half.
Okay.
So we'll be able to get a little bit more torque with these guys.
Cool.
They also do a little bit better of that micro stepping that we talked about. So that's really the only change as far as stepping goes that we have here.
So and we should talk about, so you're using you have like a microcontroller, which is the brain.
Right.
And then you typically with that situation, you have a shield or auxiliary board that is specifically for the task you want.
Exactly. In fact, you can drive stepper motors right from the microcontroller, but it takes a lot more processing, more pins. There's no reason not to offload that onto a stepper controller.
Right.
So that's what we're doing here. Which is kind of, this is the TNC board right here.
Okay.
This is a new TNC. This is the 3.6, quite long and very powerful.
It's still really tiny. It's amazing how much you can do with it.
Yeah, it's smaller than what we think of as an Arduino.
Yeah.
Like the Uno or something. It has a built-in SD card slot that we're not using. We're just using its horsepower because it has to do three things, right? It has to control the stepper motors.
Right.
It has to listen to audio and process it.
Right.
And it has to drive 2 LED strips. Now, if we had to, we could break that out into other processors, but it'd be great to tie it all into one source code, flash it, and you got it working. So that's so far. It seems like that might actually work. So this is our audio board.
Okay.
It's taking input from this cable here, which we have tied into this mixer.
Okay.
Temporarily. Now, I was hoping this mixer was a stereo mixer that would output your mic and my mic into separate channels.
So you could do the 2 paddles?
Yeah, so I don't think this mixer does that, unfortunately, but you'll get the proof of concept.
Right, which is fine.
That's reading the audio from left and right, and then drawing paddles to each of these LED strips.
Okay.
Simultaneously, it is just doing a quick ramp loop on our stepper motors just to prove that the multitasking is working.
So the motors aren't actually doing anything specific. They're just kind of like doing stuff.
That's the next step, is to actually make them play Pong, right?
Okay.
All right. So I'm going to plug this in.
All right.
I'm not going to leave it plugged in too long because this power supply is only 500 milliamps. So I'll plug that in, and then I will give power to our Teensy. With any luck, things come to life. So here we have the stepper motors are starting to run, and they're going opposite directions. And our mics, you'll see, it's not like your mic and my mic are doing the same thing.
That is amazing.
But you could imagine playing Pong. So like it would go,
That's going to be fantastic.
Right. So I guess the next step is to actually get this working so that we can actually test playing the game.
Right.
Which requires the frame behind it.
Yeah, and so I've been working on that, and I got a few ideas for that that we can reset, and I'll show you what I've been doing.
I would love to see this.
Yeah. All right, I've got a frame done.
I dig it. It's a little smaller than I imagined.
So here's what happened. We went and chatted with Adam a bit about this because I know the audience and what we talked about, the go-to is like, oh, you're basically building a 3D printer. There's tons of stuff out there for that. But we're making it, bigger than you might normally do for a 3D printer.
Quite so.
And 3D printer typically runs on linear rails and linear bearings and stuff. And so, but we wanted to we don't necessarily need that kind of precision for what we're doing.
Right.
And we wanted to keep it as simple as possible while keeping costs down.
Right.
So first thing, Adam recommends we'll make a miniature to as a proof of concept. And one of the things we talked about is using pulleys, because he's like, you can use pulleys and rope, and you can just scale it up by literally adding more rope. You can use the exact same mechanism at this size and then make it bigger and then just add more rope and, so that kind of thing.
Yeah.
So I'm in the process of sorting a lot of Lego, so I did this just for kicks. So
you made this from scratch for this thing?
Yeah. So this was a pulley proof of concept. So you basically have one axis of the gantry going, right?
Wow.
So the way it works is we just have the way I figured it worked in the real world is this would be a stepper motor connected to this, and we literally have both spindles attached to one pulley. So by doing this pulls it on left, both sides of the thing.
Wait, so each of these is connected?
So yeah, so it'd be one stepper motor that is running. So this is pulling on both sides of this at the same time. And same thing with this. We have an opposite end. You could have another motor that is feeding or taking up, and you can go back and forth.
So this is not passing through. This is wedged in
This
here.
is clamped to the wire.
Very cool,
yeah.
man.
And now I figure you could do one of two things. You could have a stepper motor at each end that would push and pull, right? Or you could even have one at the top and then either weight or a bungee or a spring or something that is just giving tension on the other end.
Right.
So there's a few ways you could go about it. This was really cool. I'm glad I did it. It was a fun proof of concept, but that is reinventing the wheel to a certain extent because there are lots of stepper motor accessories out there for what we want to do.
Right.
That would also be simpler than a whole rail system.
One thing I like about this compared to the rail system is these spindles would increase the speed, right? Because it basically goes from the center outward, and the further out we go, the more rope we bring in, and more fast, right? So we kind of trade speed for torque there.
Yeah.
So given that we had enough, this would be an interesting solution.
Yeah, and part of what I liked is the pulley system is really simple, and you can literally just get whatever, fishing line, whatever, and use it to expand it as needed. One of the things that I threw out there that was kind of crazy is hey, let's make it a V plotter, which if a little bit ago we had the Maslow CNC, which was a CNC that had two motors, and it literally uses the two motors to control the router, and it kind of is in this V cradle.
Right.
And I was like, oh my God, that'd be really cool.
When I saw that, I came in here and I saw that and I said, yeah, but how are you doing that math?
Yeah.
And then they explained everything to me, and I said, yeah, but how are you doing that math? Because it's crazy.
So V plotters they use a lot they use them for drawing a lot. So you'll have it hanging vertically, and it'll have a pen or something attached to it, and you can literally then, by changing the length of that, draw things or whatever.
Right.
And I was like, oh, that'd be really cool.
Yes, and you're right.
And it would be cool, but we're on a time crunch, so I felt that it'd be better to go with the typical XY. So
I agree with you.
Proof of concept, right? So then what I bought is I bought some of this stuff. This stuff is fantastic. It's called a few different things. The structural aluminum, extruded aluminum, T-slot aluminum.
I've seen this used in structures
you
before.
see it everywhere.
And not just for moving devices, but as just a structure for shelves and things like that, right?
This stuff's amazing. The brand name is 8020.
Oh, there's a brand that makes this?
Yeah, there's 8020 is probably the most popular.
Okay.
There's lots of other places that make it too, but 8020 has you can make anything from this, from AV carts, whole structures with doors. They have it's giant Tinker Toys.
It's designed to be modular.
Sets. It's actually a Rector set. It'd be a thing. So you can get all kinds of attachments for this, And you see them used a lot in 3D printers. Like we did the Lulzbot recently. It uses that for part of the frame. It's very popular for that kind of stuff.
Does it use it for moving parts of the frame?
Not on that particular 3D printer. So what I did is I started looking around and I found this stuff, which I got these from Servo City. These are Actobotic parts, which I'm not sure, but I think that might be Servo City's brand. I'm not really sure. But it's used a lot in robotics. So one of the things they had are these rollers that are specifically made to fit this.
Oh my gosh, that's great.
So it's got ball bearings in it, and it makes this into a giant rail.
And it goes in the middle, so there's very little friction.
Yeah. With a normal 3D printer setup, you'd have like rails with linear bearings. It's very strong and very precise and very smooth. I think for our purposes, this will probably be more than enough. Because we're not being super, super precise. It just has to be pretty good.
Yeah.
And so we're going to basically have the Pong ball riding on this gantry.
When you say we're not being super, super precise, just to be clear, we don't need to be like 1/10 of a millimeter accurate.
Yes.
If we're a millimeter accurate, that's totally fine.
Right.
Yeah.
We're still being precise, but not like 3D printer precise.
Exactly.
So basically, I figured we might be able to use these for the gantry, for the XY, for the Pong ball. So the way then it works then is that we have brackets. Actually, here we have brackets that the stepper motor could hook on to the rail.
So the motor would ride on this? Okay.
Yeah, well, we'd have one thing. We'd have one motor that has a belt going like this that rides this up and down.
Okay.
And these have little connectors that you put in the T-slot so you can screw things to it. So we'd screw this to it, we screw an idler on the other end, and then I've got little belt clamps that would clamp the belt here, and we can adjust the size.
Oh, wow.
And then it'll pull this back and forth.
So the stepper motors would be stationary,
Yep.
mounted on here, that would move this.
And I figure if there would be another stepper motor mounted to this for the y-axis. Well, if we're doing more like Cartesian, I guess this would be the y, up and down, and then x would have another motor mounted to here that would do a cross.
Okay, so this would be more like this, sorry.
Yep.
Right, and this would go up, and would there be another identical one over there?
Yeah.
Okay.
So we're going to put the frame together so we can kind of demonstrate this better.
Cool.
But there would be identical one over here, so this rides up and down.
Okay.
All right. And we have another motor attached to here that has a belt. It depends what our mechanism ends up being. The simplest is it literally is just a belt that something clips to, like the ball. We could also do a carriage, so we could put another piece of T-slot across and make an up and down carriage with another belt on it for the back and forth.
And would it slide inside this other side of it, that carriage, or would you rotate it like this so it would face outward? They'd face each other.
Yeah, we could do that.
Got it.
So I think this might work. So I want to put the frame together and hook this up and actually test it with the little controller that you made.
Great, let's do it. Ta-da!
Yeah, magic of time lapse.
Nice work.
Yeah, we've boxed ourselves in.
All right, so should we give this a try?
Yeah, so basically let's, so we have the stepper motor down here.
Yes.
We have an idler down here, which is just a spinning pulley. And then we got this little belt clamp that is clamped to the carriage here. So that means that the belt is attached here, and we got these V wheels that are riding in the structural aluminum itself.
These are super cool because there's so little tension no matter what surface it's on, because they ride right in the middle of the beam.
So I need, we have this little jury rigged right now because this isn't quite the right size belt for this clamp, so it's a little loose, but I think we're good enough to test.
All right, shall we hit the button?
Yes.
All right, it doesn't matter.
Nope.
Here we go. Oh, yeah. Look at that Pong ball go, Sean. That's cool. Now, it ramps up slowly because just for testing purposes.
It's programmed in, yeah.
But that's not a bad speed, honestly, and we're going to be able to go faster than that.
Yeah.
I'm very happy with this.
So a few things to address. This very much is an erector set. Both the structural aluminum and these parts, the Actobotic parts. You can get all kinds of different things and put them together. I think I need to get a little bit higher rollers for our purposes. And then you may notice it's kind of grindy. And that's because I'm not running this idler on what I need is like a shoulder bolt that has a smooth shaft for the idler to run on.
Got it.
It's actually running right on a screw, so it's basically grinding.
Oh, so it's right on the threads.
It's on the threads, so
okay,
yeah, it's a little grindy. But for proof of concept, I think it's okay. And this is a positive lock, and it's not going to go anywhere. And it seems to run relatively smooth.
So just from my perspective, what we're looking at here is potentially the y-axis. So this would be going up and down.
Yeah.
Using this. Okay.
Yeah. So this would be the up and down. Our LEDs will be going along here.
Right.
Right. And then what I picture, we have another stepper motor that is mounted to the carriage here.
Okay.
Right?
And that won't interfere with the belts. We're fine.
No. Well, once I get all the parts out, what I think I want to do is actually make this carriage out a little bit more and have the belt run under it so that the top is clear.
Yep.
I think that's the way to go. So we have another stepper motor attached here that then runs the belt across.
To a mirror image of what we have here.
Yeah, well, you know what? In this case, I think what we could do is have another one of these rollers on the other side, and both sides, so the other side of this will be a mirror image. So it'll have another stepper motor at the bottom of this, so that we have lots of torque, them running in
perfect
sync to move this up and down.
Synchronicity.
Yeah. For this one, we have another bar going across with just one motor.
Right.
Because if you think about it, we're just replicating what we have right here, but going this way.
And this one, the x-axis, isn't fighting gravity.
Yeah, and it's just moving. This is moving a lot more weight, and it's fighting gravity. This is just going to be moving our little pong ball, whatever that ends up being. So originally, I thought we might be able to just get away with just running a bare belt with the little pong ball attached to it.
You mean something like this?
Yeah, but I think to be safe...
If it's a ping pong ball, we could, but I want to light this up.
Yeah, so I think to be safe, we put another one of the T-slots going across that's connected to the opposite carriage, and then we have a belt on that with just an idler on this side.
That sounds like a lot safer.
Now, the only... Do you think the pong ball is going to light up interactively or just be like a battery inside kind of thing?
I'd say min spec, it lights up with a battery inside.
Okay.
Ideally, we could control the light with like the game state.
Ooh.
Right, so that if you score, it turns off or goes a color, celebrates, does something.
That gives us a good excuse to get some like cool flex cable or something to run across.
I mean, would that be the solution? We would get some sort of ribbon cable?
We could.
And it would have to go all the way to this end and then somehow fold and come back. So that's the trick.
I'll look into that.
If it can be done, cool. If not,
because it'll look cool too.
Min spec, no need.
Just matter.
It would be cool.
That's like on the dream list. Okay, so this is our test frame. This one's 4x4. So we'll have to figure, but the nice thing is the whole way this is laid out, this is an open-ended belt. So that means we could add, you can get this up to 8 feet long. So you could add, you could add twice as much and just add the belt and it's gonna.
We could make this 8x8?
If we wanted to.
All right.
You're just adding more belt and it's just gonna keep riding along the track like it is now. So, and then, I'm assuming we may wanna put in some end stops to.
Well, not necessary. We could actually put it in our home position and then turn it on.
Yep.
It would know, given that this is a 1 day only use case. But if we wanted to be fancy and have it home itself when you turn it on, we could do end stops.
Okay.
So again, min spec not necessary. Dream list, yes, end stops are good.
Yeah.
But only need one. Because if we can't detect, that's the magic thing about stepper motors, is we know where the end is. As long as we know where one end is, we know where the other end is.
Right.
If we don't, that means we're losing steps and we have a bigger problem because then we don't know where the ball is.
Okay, got it. So I think this is a good solution using the minimum amount of hardware.
I love this solution.
This is avoiding having to use rails. I mean, this is the rail, but rather than we don't have to get into bearings and all that kind of stuff. So do you feel fairly confident with this?
Having just put together a 3D printer, I'm amazed at how little friction there is from this guy.
Yeah.
I think this is the ideal solution. This is fantastic. It's super modular, so if we need to make adjustments, it's easily done.
Exactly.
We can take it apart, bring it places.
Yeah.
I love this idea. Well done.
Okay, good. So what I'll do is I'll order a few more parts to make this a little more elegant,
Okay.
and to figure out exactly how we're going to attach another beam.
The x-axis.
So I'm thinking, so we're looking at 3 stepper motors.
Got it.
So 2 in sync and then 1
Yep.
further across. So does that sound reasonable?
From what I've seen from 3D printers, the ones that are in sync can drive off the same driver. So we'll still only need,
that's great.
So we'll still only need 2 drivers. No. Wait, is that true? No. They take the same. I'll look into this, Sean.
It's like the same signal?
I'll look into this. This
Okay.
is more learning opportunities.
Okay.
In any case, that won't be a problem because it's done all the time on 3D printers.
Cool. And,
yeah.
And also, for those of you like looking to build something like with the structural aluminum, I know at least the 8020 site, you can actually download a CAD plugin for like AutoCAD and other programs that will let you have all the parts.
Oh, wow.
So like building with Lego. And
Yeah.
you can literally like try test fitting things together and see how it's going to work before you actually buy the stuff.
And-
Because the downside of this, it's not cheap.
Right.
But it's really, really cool.
And you said you can buy it as a kit so that you know it's going to be compatible. All the
Yeah,
parts.
it's like when you go to the page, it's like all of these brackets and everything on this page are made for this.
Cool.
And they have, this is 1 inch. You can go up to bigger, like 1.5, I think maybe even 2 inch. And they even have double ones where they're
neat.
double wide for like, I think the X-Carve uses some of the heavier, like big stuff. But fantastic stuff to build with. It really gives you a lot of flexibility.
Well, we're well on our way here. I'm super excited. My next step is going to be to actually get some Pong code running,
Okay.
which will be interesting to develop without being able to test it. So I will be looking forward to our next exchange.
Yeah, that's the interesting thing about doing these.
Yes, with much
Certainly.
anticipation.
Yeah.
So I'll let you know when we're ready to do that. Maybe another couple weeks. We only have 1 more month before the live show.
I think we can do it.
I believe we can do it too, but I also have seen we have run into problems before. So fingers crossed, the problems won't be roadblocks.
Yeah, I think we'll be all right.
All right, good luck. Sean?
A lot has happened since the last check-in.
Right. So here we are. We are 4 days from the live performance.
Yeah.
And as you said, a lot has happened. So when last we were here, we had the basic structure working with
had
a couple steppers in motion, right?
Yeah, we had a 4x4 frame as a proof of concept.
Yes.
Uh-huh.
Then I went to work on a circuit board because the first thing that I wanted to do after playing around, bringing the breadboard here, was get rid of that thing, man. Because I don't trust breadboards at all.
You could lose a wire, or lose
Exactly.
connection.
They're great for prototyping.
Yeah.
And honestly, like this is a one-time thing. Maybe it would have been okay, but I just had these nightmares of bringing the thing to the theater and losing one of those hookup wires and
Yeah.
forgetting where it went. So
So when you said you wanted to do that, I was
Yeah.
like, that seems like a pricey thing to do for this, but it was really reasonable.
oh yeah, no, especially these days, it's just gotten easier and easier. So I actually submitted the design to a manufacturer in China on Monday, and I had the boards on Friday. And super simple. It cut the bread. The breadboard would just be like this big, and cut it down to this size. Everything's soldered together, so it's much more, permanent now.
And was there like a minimum order you had to do or something?
You have to get 5.
5.
Yeah.
And so how much did that end up costing?
$40. Yeah, very reasonable,
you
right?
cannot beat that. Great.
No.
Worth every penny.
Definitely. So while that order was being manufactured, before I was able to assemble it,
Yeah.
I came over to your house.
Yeah, because it's funny because we don't particularly live close to each other, and the nature of what we work, our workshops are at home.
Yep.
So we've been in our separate camps working on mechanical and the software. We have to get it together to work. So at that point, and we'll cut to some magical B-roll so people can check this out. But we did the 6 foot by 4 foot frame is kind of what we decided on.
Right.
And I had a shorter version of that because I hadn't done the tall legs yet. So we tested that out, and it worked really well.
That was the first test of the code proper, like actually playing Pong.
It was awesome.
Yeah, so and that was when we finally saw that working. It was such a relief. And there was one small trigonometry error that I had to fix right on site. I was able to pull the laptop out and do that. But that was the biggest challenge for me, was actually having to code the game without being able to see it.
I was really impressed by that because that's really just trusting your numbers.
Right, and that's exactly what I had. It's like I would print out in the debug console where it thought the puck was at any moment.
Right.
And I would just say, okay, that seems like it's going higher. That seems like it's going to the right. But I couldn't see it. And it wasn't until I came over to your house and we put together the first real functioning, build that I was able to see that trig error and make the fix.
I'm glad you had to do all the math. So
but tell me about the parts that you decided that you needed to get in order to make the structure work.
The interesting thing is, I ordered, we had talked about you getting the Actobotics hardware, which are the rollers for running in the track here.
Right.
And this is the extruded aluminum framing, which we stuck with the same hardware that I initially bought, but we just blew it up bigger. But that was part of the advantage of working with this stuff, is that you can slide things around and just by adding a little more belt or whatever, make it as big or small as you need. So it's scaled really well.
How big can you buy these beams if you want to?
I think you can go up to, I know definitely 8 feet. These are 6.
Okay.
I think you can go up to 8, if not 10.
Okay.
At the time when we tested it, we had one motor on the long axis here and then one on the Y. And it actually totally worked that way.
Well, it did work, but the bottom would sort of drag behind.
It had a little bit of a pendulum motion when it started up. So we did add a second stepper on the bottom just to make things smoother. And I think that was a really good call.
Works great.
And it wasn't too hard to do as far as I understand, adding it to the code.
We had always intended, one of the original ideas that we had was this would be a vertical game and it would be rising. So we had thought about having 2 steppers on the Y-axis. So I had already coded that. So just putting 2 on the X was no problem at all. The only problem that it actually caused was when I submitted the circuit board, I only had 1. And then 6 hours later, I was like, oh no! Oh no, I need to add another stepper. And so I added it and resubmitted it. I only had to pay 1 shipping fee, but got both circuit boards.
That's good.
Yeah, but both X work great now. So now the entire thing is in sync. And this would be a great time to show it off.
Yes, absolutely.
You want to bring it over?
Yeah, so we, with the steppers disengaged, we can do it. So we have, like I said, one on the top, one on the bottom, and we just kind of home it by pushing it to one end. We didn't go too fancy. We didn't do end stops or anything like that. We just are doing it by hand.
Normally, like a laser cutter or a 3D printer would have switches at the end of the extremities, so that the machine knows that it's hit the end.
Yeah, but for our purposes and what we're doing, that was a little overkill and more components to add and fail and fiddle with.
Right.
So we just home it by hand and we type and you put in the numbers so that it doesn't crash.
You know how many times this has to work, right?
Right.
Once.
Right.
But, so you designed the puck.
Yeah,
I think it's a pretty great design.
The interesting thing about, we went through a few mechanical layouts.
Yeah, that's right.
Originally, these belts were going to be on the side, and this bar was going to go across. But then, when we kind of flipped it, so it was going to be this horizontal. It made more sense to do this. And actually, the whole time we've been working on it, all of this stuff was on the front. So this bar was on the front, and then the more we worked on it, we were like, wait, it would actually visually look better.
Because where do the LEDs go?
Right.
Do you want the LEDs to be behind the puck? I mean, that would be kind of interesting, but then you'd obscure them. What makes the most sense from a playability standpoint? We had to ask these questions.
So we literally just flipped this around. That's why originally these braces were on the back, but it wasn't worth moving them at this point. And that actually allowed for the puck to be just kind of floating on the bar, which I think is better. And we also had a lot more structural stuff I had intended because our smaller version that didn't have the legs was really, the frame really was flexy, and I was concerned about that.
Right, we talked about maybe having a center beam here in order to make it more rigid, but it seems like it's okay.
Yeah, and I even bought bigger cross braces here, and once we got the big legs on and it grounded and everything tightened up, it's rigid enough for our purposes. So that stuff could go back.
Right.
So the puck then is magnetic.
Love it.
So the carriage wheels are sticking out here, and the top of the screws for the carriage are there. So originally I designed it to be hard mounted, but the more I thought about it, one of the problems we run into is that we had to keep in mind is this has to be disassembled to get to the event. So I had to think about how does this go together and come apart, and I was worried about having the plastic puck on there and getting damaged and or having to screw it on when we got there. So our friends, have used magnets in so many projects.
Right.
They're like the best.
I love that you've gotten so comfortable with them.
They're great.
So you have magnets not only to secure it to the actual transport mech, but you have the cover that actually secures itself to itself with a battery inside and a power switch.
And it's great because, and we've talked about this kind of stuff before, a lot of this mechanical stuff, this is all from Servo City, they post the CAD files. So if you need to design something to fit it, you can download these and you have you can get it exact.
Yeah.
So I loaded in the parts into my program so I could lay out the magnets. And we just did a simple open space with, these are our favorite 1 watt LEDs that we use on the Ghost Trap. So really bright.
I thought we might need to go 3 watt. That is plenty bright.
Yeah, and we just have a little on-off switch inside. You magnet it on and magnets on, and it'll run for a few hours.
Awesome.
And I think that, it worked out great.
So another change that we made was the actual
the
treads, the belts, right?
Yeah.
Because you wanted to get ones that fit more accurately?
Well, there's a few reasons for that. So the interesting thing about this is you're kind of I had a vague idea of how this should work.
Yes.
But it's one of those things where you have a vague understanding of how your car works, but if you needed to build a car,
I have a vague understanding of how my light switch works.
Yeah. So I knew a lot of stuff that needed to go on. This was vaguely like a 3D printer or a plotter.
Yeah.
And you had bought some just a pack of stepper motors and belts and pulleys.
Yeah.
Off of
Amazon. In
Amazon.
fact, I chose them because they were well priced on Amazon. Yeah. And they were the belts that people had bought with those steppers.
Yeah.
That's it. Yeah.
And they actually worked fine for our testing. But the Actobotics system has specific clamps for the belts and stuff. And what happened was this is like the original belt, which has really fine teeth on it. And it's obviously thinner than what we have now.
Yep.
And they didn't clamp well. I was also a little worried about these really fine teeth over such a big distance. I was worried about the teeth possibly slipping. So we got this much heavier belt that has really big beefy teeth on it.
Like tank tread.
Yeah, and the belt's a little heavier and it perfectly clamps now. And I felt like they wouldn't slip as much on the pulleys here.
Well, and we had to change the pulley to have a different number of teeth.
Yes.
Which it turns out, I didn't know this, it makes perfect sense, but it turns out that that changes the distance that it travels based on how fast the motor turns.
And I kind of ordered these before, we didn't know.
Right.
So I ordered these and you're like, wait a second, that changes things. I was like, I had no clue.
Right, well, luckily that was the easy code change. I had a variable in there that was steps per millimeter. And there's a wonderful calculator online on the Prusa website, of all places.
Great.
Where you can go and type in your motor and your tread and your pulley, and you get the magic number.
Yeah.
So that was a matter of just changing that, and that worked out fine. The only problem was actually this pulley has 10 teeth. Is that right?
Yeah.
And this is an Imperial pulley and belt brand.
Yeah.
And so it didn't line up to an even number of millimeters.
Of course not.
However, it's such a small difference, it doesn't really matter.
Good.
Yeah.
That was one more change.
Then what we wanted to do is find out the distance in millimeters between the goals. And
right.
That's actually the final code change that we need to make at some point today. Right now it travels and it's pretty close, but I'd like to dial that in.
Because we were a little conservative so it didn't bash into the sides or anything.
Exactly. And it should go top to bottom pretty well. We actually have maybe 100 millimeters of extra space on the top and bottom of the LED strips.
Yeah.
So as you said, we actually home it by hand.
Yeah.
So the system thinks that it's going to be at the 0, point on the grid, which is over here at the bottom of LED when you turn it on.
Right.
And then after you turn it on, it should rise to the center of this goal, and then it's ready to play. And then the system just assumes that it's right. Like it'll send the puck to a space on our playfield here,
right.
But there's nothing on this playfield to tell it if it's correct.
So if we don't home it proproperly, it'll wreck itself.
Right, it'll be very noisy,
right.
And it'll just stupidly jam itself into walls.
It also, we're going to have to fire this up. We've been burying the lead, but talking about the code a little bit. So, you're basically creating all this from scratch. Did you Pong's been around forever?
Yeah.
So was there like a standard Pong program that you could just plug in as a base? Or
no.
Did you just start from scratch?
No, I started from scratch, but it's Pong, dude. I mean, it takes a day to code Pong. If you're me, if you're good, it takes you an hour. But if you're me, it takes you a day. And the interesting thing about the code for me was when I've done Pong-style games and Breakout, like the Game Frame has a Breakout-style game on it.
Yeah.
I've always just sent things in a direction, and then I've checked every frame to see if it's at the edge of the screen.
Right.
And if it is, then it'll ricochet, or it'll score, or whatever it has to do. With this, the way that the stepper motor library works is it doesn't want to go in a direction. It wants to go to a destination. So what I had to learn, just a little bit more trig than I knew, which was to not only send it in this direction, but to know what this point is. So if it's going in that direction, it not only, I know the distance between the puck and the ceiling, and I know the angle it's traveling at, and giving those two figures, I can find out when it crosses the line.
Okay.
So I just sent it to those points. So every time you see the ball moving, it's been sent to a new destination, and when it ricochets, it's sent to another destination.
That's an interesting question also. When it ricochets, how does it determine the angle of the ricochet?
For the top and bottom, it's standard Pong. It's just an inverse of your angle.
Okay.
So if you come up at a steep, it'll repel at a steep. Shallow, shallow. On the pucks though, also true to the game, where you hit on the puck matters. So if you hit at the top, it'll ricochet up and back, and if you hit bottom, it'll go down and back. In the middle, it's more of a straight lateral shot.
Cool.
But our puck does never increase in speed.
It's linear, right?
We're always going as fast as we can. So I think if we were to change the steppers or something like that, or the belt, or find a way we could make a faster game.
Yeah.
I don't think that's a problem.
I think for our purposes, for the audience, right, this will be perfect.
Yeah.
So I feel like we should fire it up.
Should we do it?
Yeah.
All right. Okay, so real quickly here, these are the 3 stepper motors here.
Yeah.
And I added a couple things that we didn't have on the breadboard before. One is this cool little dial/button.
Nice, I love those.
So this is a rotary encoder. First time I've ever used one before. It's super cool. So it rotates infinitely in either direction, and there's a button on it, and we'll use that to actually calibrate the game.
Awesome.
These are our 2 audio inputs and outputs.
Yep.
So I'm going to take the microphone here and plug it into the line in.
All right.
From our new mixer, courtesy of Kishore.
Thank you, Kishore.
That actually has stereo. Everything else should be ready to go. So if we want to home the puck.
Yeah, so this, once we set, again, we just do this by hand.
Yep.
And I believe we're just doing it right in the middle of the strip.
We want to home it to the bottom LED. But yes, horizontally in this, yes, exactly.
And then right about there.
Yeah. Man, get it. We want the center. So what's interesting about this game is that it actually tracks the center of the puck.
Right.
Yeah, so it's a little bit like, that's how it works. But like, I think it's possible we might get some audience members saying, I hit that, when actually they missed the center. They just hit the edge.
Right.
We're not calculating edge here, just center.
Yeah.
They'll forgive us for that.
We can fill them in.
Okay. So real quickly, the power for the circuit board, that was sort of an unknown. Given that we had sort of one shot to get a circuit board right,
I
left 3 options. One, I threw on a little regulator here to convert 12 volts down to 5.
Right.
Totally wrong solution.
I recall, well, on our test, I recall that getting very hot.
Very hot. Okay. In fact, it was shut down. It was very unhappy.
Okay.
The other solution as a backup was to just do a second barrel jack here. Didn't use that. I used these little pads here to run to a buck converter on the back here that actually changes the 12 volts down to 5.
Nice.
So happily, we can run the whole system off a single 12 volt source, which I will plug in now.
Excellent. I recall during our testing also that there were some issues with making sure everything was plugged in before we powered up and not unplugging things when it was powered up.
Yes.
Because it can fry.
We actually had the wire rip out a couple times and nothing fried.
We bent some pins, but
we did bend some pins.
Nothing fried.
All right, so here we go. I'm going to plug this in. If everything is hooked up properly, nothing should happen because I have a new power switch here for the 5 volt.
Oh, good.
So I'm going to turn that on now.
Look at that.
There it is. So now we have a homed puck.
That looks about right.
Excellent. Here,
we already have paddles going.
As you can see, we have stereo paddles. So check. That one's the right. So that one's over there.
Check.
Right. So check. All right. So now we have what could be an actual functioning game, except we can't serve the ball.
All right. We got
without
a paddle.
The paddle of serving.
I love it.
If you could please hold the paddle of serving, I will plug it into the circuit board. Do you hear that?
No.
Okay, I thought I heard a little spark.
Okay.
Okay. Now, the first thing we should do is calibrate. So I'm going to actually,
Here, I'll let you hold the paddle since you're closer to the
we
board.
have an advantage that the audience won't have, don't we?
Yes.
We can actually get closer to the microphone and further away from the microphone to control how loud we are.
Yeah.
The audience is going to have to actually get louder. So that's something else that we can't do a real good test on.
We've talked about this from the beginning. There's not an easy way to get 1,000 people together to test this.
Exactly. So I'm relying on this calibration process to work in that case too. So let's give it a shot. So the first step here is I'm going to click this red button, the red dial, and we're going to set the low end. So this is how loud do you have to be to get any kind of signal to start the paddle rising.
Excellent.
Right. So if I were to raise that way up here, it would stop rising because it needs a louder level to actually trigger anything.
That is excellent, Jeremy.
So let's set it, for our purposes, I'm going to set it here. Yeah? Okay, and then we set the top end, the same thing. So how loud do you have to be to hit the top? I'm going to go there.
Yeah.
Right?
That is such a nice touch, Jeremy. That's great.
You got to calibrate it or else it's not going to work.
I know, but it's really well thought out. I love the little indicators, everything. It's great.
Yeah, so then we have a brightness setting, which, for the show, we'll set it nice and bright. For this performance here, we'll probably set it a little lower. And then we're ready to go. Are you ready, sir?
I am ready.
Oh, I almost forgot sound.
Ooh.
So we'll plug into the Castro sound system, hopefully. Until then, I have this little speaker that plugs right in here.
Well, you actually added sound effects too.
Of course.
Oh, great.
If this goes in, there we are. All right, hopefully we'll hear something, and
Woo!
here it comes. It's over to you.
Oh, this is so hard.
There we are. Now, hopefully the audience won't break the game by making the other person, oh no, fail! Now, the audience, hopefully, they won't be able to control their opponent's paddle.
That's a complete unknown, yeah.
So hopefully we'll be able to calibrate it such that loud on left does not have an effect on right's paddle.
Right, because otherwise it's going to get real interesting.
One of these unknowns, man. All right, point 2.
No, that was close.
Wow, you're good. I don't think I have to do anything here.
Nah, I think you're good.
Nice angled hit. Going off the ceiling. Back down. This is a tough one.
Oh! It's harder than it looks.
No, it is. It is. And it does depend on the calibration. Like if you have more or less. And who's to say that like this isn't harder? Maybe it's like there's too much variation here, and actually making loud noises as opposed to making the mic closer.
I feel like we may want to give the audience some have them say up or something, like give them some kind of like thing like
I
to
totally
do
agree.
together. Like otherwise it'll be all over the place.
They need something to say.
Like up or something.
Right. Like say left or right or up.
Yeah.
Yeah. All right. Here we go. Oh, I didn't mention we can change the size of the paddle.
Oh,
you want
nice.
to be super easy?
Oh, yeah.
What happened?
Oh, no.
Oh, that's interesting. Wow. I'm glad that happened here.
Paddle change.
No.
Oh,
wow.
froze.
No, the system definitely froze.
Interesting.
Maybe it was because of the paddle change.
And you're here.
Oh, wait. You know what it was?
What?
You're at the top.
Yeah.
I've only tested changing the paddles when you're at the bottom. So it extends it, and it went off the strip.
Which is like, does not compute.
Okay, that's good to know. So we will only change paddle size before anybody's served.
Yeah.
Oh, wow. That's great. This is good testing. We have 4 days. All right, so what that means is we actually have to reset. We have to reboot the whole thing. I'm going to unplug.
All right.
Look, you're generating power. Did you see that?
Oh, nice. Some of you may be wondering, we got these 2 stepper motors and we're just pushing this over by hand. You can actually get it out of whack, like off axis in comparison. We're just eyeballing it, which we have found has been fine for our purposes because this isn't a super precise machine like a 3D printer or something, so that's been working fine.
All right, so one more test here of the paddle size. We can go super big, or, and then it still works. Like you still have to be as loud as before to go to the top.
Yeah.
And that's just easy. So if the audience is really bad at this, or if the game just is not good at picking things up, we'll make it easier, like this. Or alternatively, if they're amazing.
I like the idea of like, oh, you guys are doing pretty good. Yeah.
Yeah. Now let's see how you do. Let's try this.
Once again, a very nice touch that you've added. Oh man, this is way harder. Oh, that's much harder.
You could have been quiet. That's the funny thing. I disagree. Who coded this game? That's horrible. That was totally odd.
That did look like a center hit. Yeah. You might have to check that out.
All right. I might have to check that out. You know, we do have that one debug mode. Let me show that real quick here, where if we unpower and we home. That's why you should do
See, but that's good because it's breakaway. All right.
So push the frame, not the light. Mm-hmm. There we go. I'm going to say we didn't home it properly. So now, with our debug mode, we can actually see where the system thinks the ball is.
Oh, good.
So if I hold this button in, it will just automatically... Oh, right, I have to... So now this blue light is where it thinks the puck is, and it will just serve its own game.
No way. Oh, that is amazing.
So now it's over there. Does it seem like it's in line?
That looked pretty right on.
Here, I'll make this real big so it will... Yeah, that's right on.
Nice. I might not have homed it quite. Is it the center that should be at the end, or the edge that should be
The center should be in the center.
Okay. And also, so one of the other things that we should put on, we put these acrylic panels in, and part of the reason we moved the gantry to the back is that so that the puck could actually pass beneath the paddle, which visually looked better. Yeah.
You might be able to see the blue light a little bit better now with that smaller puck. It seems like it's in line. I'm happy with that.
No, that's good.
All right, man. What do you think?
I feel like we're ready. Like you know, I think we need to, like you said, do a few tweaks on the field size, and mechanically, I think we're pretty good. And I think we figured out how to dress the cable so nothing gets caught. Mm-hmm. We do have to disassemble this partly to get it in, but we kind of worked that out ahead of time so that I have ways to take it apart without too much trouble. So
good.
Yeah.
So assembly maybe a half hour. What do you think?
Yeah. I think so.
Okay.
Yeah.
Well, fingers crossed, man. There's still one more thing left to test here, and that is having 1,000 people play the thing.
No pressure.
Yeah, right. No pressure. I mean, that's something we can't actually test until we're actually there. But I have never been more excited to show off a project than I have this one. And so I'm super excited that it's going to involve so many people to play it with us.
Yeah, you had a great idea, and you have a really good knack for coming up with fun, interactive projects, which are not normally things I come up with. Is part of why we're a good team. And I think regardless of how this turns out on stage, the audience will be entertained.
Well, yes, it is certainly interactive. Whether or not it's fun or not, we will find out in 4 days. So fingers crossed. I actually have a little bit of faith in this one, which that concerns me. Nonetheless,
we'll be good.
Yeah, we'll see you in 4 days. Just this week, we finally put everything together, and miraculously, it actually seemed to work. And I don't know, Sean, I'm kind of waiting for the final shoe to drop here because this has gone too well so far. What do you say we actually power it up and play a game?
Yeah, I think we should. All right. So Jeremy's going to initialize this. It would be cool to play this and everything, but the last key thing is we're like, well, it'd be fun if we play rather, but we're going to have you guys play it for us. And
if you're up for it. Are you up for it?
Yeah.
All right.
And we're not talking about like one representative. We're like talking like the whole audience. So we're going to fire this up. We're going to do some calibrations, and then you guys are going to make these paddles go. So.
All right, so what I need at first is just to do a quick level check. I need everyone to give me, let's say up for about 5 seconds. So like up, as loud as you can. Just 1, 2, 3, up. Great. All right, now let's do the one side here. Oh, yes, very good.
So this is actually the custom circuit board that Jeremy designed and sent off and got printed for this project. So if you haven't figured it out yet, the louder you are, the higher the paddles go.
Yes.
So, yeah.
All right, so now we should actually be split. Can we have that side give an up for a couple seconds? 1, 2, 3.
Sort of,
wow.
I think maybe a little higher there.
That's
Yeah.
horrible. So
we'll get this dialed in. So also,
that's crazy.
Talking about building in the dark, it was a little hard to get 1,000 people together to test this beforehand. So this is like real live like troubleshooting here. So yeah.
No.
So yeah, we got these mics here to pick you guys up.
Okay, you know, it could still work. It can still work.
Yeah.
All right, let's give it a shot here. Where's our paddle? Here
It's right down there.
There's our paddle of serving.
All right, so.
All right, so.
We'll try going to 5.
We're going to have this side, we're going to serve over to you guys. The louder you are, your paddle will go up. You ready? Here we go.
Oh, that was really fun.
That was him.
Taking you down from the inside.
All right.
Yeah, so, all right, we'll be quiet.
Here we go.
Let's try
Over to us now.
That didn't count.
Oh, so close.
So close.
All right. Third time's the charm, I know it. Here we go.
Yep.
Oh my God.
All right.
What do you think?
So they're just getting warmed up. They're getting warmed up, yeah.
You don't think we need to change anything?
Let's try one
here
more
we go.
time.
Here we got this.
Let's try one more time. Oh.
Yeah!
1 point.
Oh! That was close.
Now,
do you guys want a bigger paddle? We can do that. Yeah.
2-1.
Yeah. This is too easy.
Yeah.
There we are. Someone messed you up.
I think you're getting
Someone
some
did that.
sabotage. There's some sabotage going on over here.
They
and
figured
it wasn't
it
me
out.
this time. Yeah. What is that? Are we at 3-2?
Anyone keeping score?
Yeah, I'm supposed to be. Yeah.
All right. What do you say? One more?
Yeah.
All right, one more. Here we go. Game point.
Oh, so close.
All right. That's our MECHA-PONG, people. Thank you very much.
Thank you.